Welcome to our presentation on fast simulations of air conditioning systems using Spline-Based Table Look-Up Method with Analytic Jacobians. My name is Lixiang Li. I am a simulation engineer at Modelon. It's great to be joining everyone here virtually. I hope this new conference format can reach a broader audience and can spark some inspiring discussion during the Q&A session. Before I start, let me acknowledge our team for this collaborative work between Ford Motor Company and Modelon. Jesse Go, Dr. John Batey, and I worked on the implementation of the refrigerant property models. Dr. Christopher Greiner and Dr. Kai Wang built the complex system models to test the new refrigerant property models. This project is a continuation of our previous work on spline-based table lookup method for refrigerant property, presented 2 years ago at the first American Modelica conference. In today's talk, I'll be focusing on enabling analytic Jacobians in refrigerant property model and using it to speed up simulations of air conditioning systems. We'll first go over some basics on analytic Jacobians in system simulation, followed by a quick review of the spline-based table lookup method, SBTL. With those background knowledge, we'll then move on to how we actually implement derivative functions for refrigerant properties. I'll close the talk with some results showing the speed up in system simulation by using analytic Jacobians. Property calculation is at the core of speeding up dynamic simulation of two-phase systems. Typically, refrigerant property models are based on multi-parameter equation of state, which is very costly to evaluate. Internal iteration is needed if the equation of state and the system model use different sets of state variables. And we have to perform these function evaluation and iteration many times in a dynamic simulation. To address these issues, we apply the SBTL method to refrigerant property models in Modelica and cut the simulation time in half for complex system models. At that point, we ask ourselves, what else can we do to push the performance even further? In the past, we have seen over 100 times speed up in very complex thermal power models when analytic Jacobian is used. With a spline-based formulation, it's easier to write the derivative functions compared to doing that for a multi-parameter equation of state. And that is what we have done for this project. Let's first take a look at analytic Jacobians in the context of system simulation. The Jacobian matrix of a vector-valued function is the matrix of all its first derivatives. There are two critical places where the Jacobian matrix is used in dynamic system simulations. The first one is solving nonlinear system using Newton's method, where the Jacobian appears in its iteration scheme. Jacobian matrix might also be required by an implicit numerical integrator, for example, the frequently used Dassault-Solver. With analytic Jacobians, we get more accurate function derivatives, which leads to faster convergence on nonlinear systems and potentially more robust models. So, Modelica compilers apply automatic differentiation to construct the analytic Jacobians. However, there are many ways in which automatic differentiation can fail. Common issues include multi-line Modelica functions without appropriate information for the tool to perform automatic differentiation, or external code without derivatives provided via the annotations. This is exactly how many property routines are implemented in Modelica. To obtain analytic Jacobians, the model developer needs to provide the derivatives to the property function and use the right annotations in them. Now let's switch gear to the spline-based table lookup method. The spline-based table lookup method, or SBTL, takes advantage of a specific type of quadratic spline on an equidistant grid. A 1D example is shown on the right here. Each piece of the spline goes through a data point, called the node, and two neighboring pieces join smoothly together at the knot. With the equidistant grid, we don't have to search when we evaluate a spline at a particular point. Since the spline is quadratic, it has analytic inverse and continuous first derivative. These property makes it an ideal candidate for refrigerant property modeling. Applying the SBTL method, we can represent the thermodynamic properties of a refrigerant by 4 different spline fits. First of all, we can describe the phase boundary by a 1D spline, saturation temperature as a function of pressure. In the single-phase region, we can represent temperature, density, and entropy by 3 different 2D splines. In the two-phase region, we use mass-specific property calculated based on vapor quality. Other properties like specific heat capacity can be derived from 1D and 2D splines. Now, one of the key features of an SBTL refrigerant model is that the saturation enthalpy functions are not simple 1D spline of pressure. For a consistent phase boundary description, they're implemented as inverse function of the 2D temperature spline, and this has a consequence when we want to write the derivative of them. The other key feature of SBTL refrigerant model that affects how we formulate its derivative is the grid transformation. The use of equidistant grid removes the computational overhead of searching through the grid when evaluating the spline. However, it will require a large number of data points when the function is highly nonlinear. Even worse for 2D splines. By introducing a proper coordinate transformation, we can get a good fit on an equidistant grid with a reasonable amount of data. For example, we can apply a log scaling on pressure. Now, due to this grid transformation, we have to apply chain rule when calculating the derivative of the spline. Let's take a look at a simple example. Here we scale pressure using a log function and call it P bar. Then we fit the saturation temperature on the P bar grid instead of the P grid. The transformation gives us a better fit over a wide range of pressure, but it also complicates the derivative. As we can see, an additional 1 over P term appears in the first derivative because of the chain rule, and the second order derivative is even more complicated. After reviewing the basics on analytic Jacobians and SBTL property models, let's now talk about the actual implementation of refrigerant property model with analytic Jacobians. The first step is to identify what derivative functions are needed by the compiler to construct the Jacobian matrix. 2 advanced flag in Dymola can be used here. With the first flag set to true, Dymola will try to construct analytic Jacobians during compilation of the model. When Dymola fails to do so, the user can set the second flag to true to find out what derivative functions are missing. In our case, we started with the twin evaporator cycle model in Modelon's air conditioning library, and we identified a few missing pieces. As you can see, we not only need to take care of the derivatives in the refrigerant property models, we also need to keep an eye on other components in the system, like the compressor efficiency functions. Among all these missing derivatives, the saturation property are the trickiest. There are some subtleties I would like to address here. Recall that the saturation enthalpy functions are not implemented as simple 1D spline of pressure. Instead, they are implemented as inverse function from the 2D temperature spline in order to get a consistent description of the phase boundary. So, their derivatives must be constructed from the derivatives of the 2D temperature spline and the 1D saturation temperature spline. Here's the example of the first derivative. As you can see, the first order derivative of the 1D spline appears in the second term, and the partial derivative of the 2D temperature spline also appear in the expression, and we need to evaluate these derivatives at the phase boundary. The second-order derivatives will look more complicated, but we can derive them in the same manner using chain rule. All right, now comes the moment of truth. How fast can we get with analytic Jacobian? We'll first take a look at a simple heat exchanger test and two system models from our air conditioning library. We'll then move on to a complex 3-branch air conditioning system and another AC system coupled with a cooling loop, both developed at Ford Motor Company. This is the hardware and software configuration we used for our test. We used the Dazzle solver in Daimoler 2018 FD01, and the tolerance of the integrator is set to 1E-6 to ensure mass conservation. The first test is on an evaporator model with 18 discretized volumes and 56 dynamic states. We ran it for 20 seconds with a ramp in the refrigerant mass flow rate started at 5 seconds. Comparing the green line to the magenta line in the CPU time plots, we can see that the use of analytic Jacobian cuts the time by 17% compared to the original SBTL model. That's a good start, right? Let's up the game. The twin evaporator system from the air conditioning library comes next. It has 131 states, and it has a 10 degrees Celsius ramp in the inlet air temperature at the evaporator from 90 seconds to 100 seconds. In this test, simulation with analytic Jacobians get a 1.7 times speed up. Let's keep the speed up going. Now we are looking at a cabin pull-down test from the air conditioning library. It has a 4-component AC unit with superheat control TXV. It also has a variable displacement compressor, and the displacement volume is controlled to get a targeted air temperature out of the evaporator. This simulation ran 2 times faster with analytic Jacobians than without. Up to this point, we have seen promising results in relatively complex systems. But the dynamics are simple, mostly triggered by a ramp in the boundary condition. Here we have a 3-branch AC system developed at Ford. The superheat out of the 2 evaporators and the chiller are controlled by the TXVs. The condenser has an internal receiver in it, and tabulated boundary conditions are used to represent the SC03 drive cycle. Fast dynamics are introduced by rapidly closing the valve upstream of the chiller TXV at 100 seconds, which results in a low flow rate condition in the chiller. The green line in the CPU time plot shows the performance of the SBTL property model with analytic Jacobians. In terms of total CPU time, we have a 4 times speed up compared to the original SBTL property model. The more intriguing thing, however, is how smooth the CPU time looks through the simulation, even when the chiller is experiencing a low flow rate after 100 seconds. Normally, a low flow rate condition is the most challenging in dynamic simulation. That led us to test the new property model in extreme conditions, zero flow and reverse flow. Here we have a vapor compression cycle connected to a cooling loop. The system is initialized with a certain flow rate, and the compressor is immediately off at 0 seconds. At about 22 seconds, the flow rate in the chiller goes to 0. The solid mass connected to the cooling loop is experiencing a constant heat flow input, and the temperature of it keeps rising, heating the refrigerant in the chiller and creating a super tiny reverse flow. The compressor kicks in when the solid temperature exceeds a certain threshold. In this challenging test, we achieve a 14 times speed up in total CPU time. More importantly, if we zoom into the tiny reverse flow condition from 22 seconds to 122 seconds, we spent only 1.34 seconds of CPU time with Analytic Jacobian. That is 125 times speed up compared to SBTL medium without Analytic Jacobian. In summary, we developed SBTL refrigerant property models with Analytic Jacobians. We have seen 2 to 4 times speed up in complex system models. An even greater performance boost was observed in drive cycle simulations and in challenging low and reverse flow conditions. We are very excited about the speed up brought by Analytic Jacobians, and we are proud to announce that these property models will be available in the upcoming release of our air conditioning library. Thank you for your time, and I look forward to talking to you in the Q&A session.